Hi, this example problem shows how to calculate the moment of inertia of a baton and for two different axes of rotation. Pause for a moment so you can read the question. All right, so you can see a picture of the baton there. So it's got the thin rod and it connects two end caps of masses. So really we're talking about kind of three different objects here that are all stuck together. If I label these, the rod is one and then the two end caps are the other objects. So we got three total things. In part A, we're going to go calculate the moment of inertia if we want to rotate the rod about an axis that goes through one end. So to show what that means for part A, what we're going to do is we're going to go ahead and show you where that axis of rotation is here. So here's our baton. And what we mean about one end is that in and straight out of the page here, there's an axis that goes through one of the ends that I marked. And we can rotate the baton in a big circle with this end being fixed in place, right? So we want to calculate what the moment of inertia is here for this rod. Now the first thing about moment of inertia is that the moment of inertia, if you have more than one object that's rotating, you have to add it up for each individual object. And so in this case, we've got I1 plus I2 plus I3 because we've got the rod and the two end caps. Now we need to look up the equation for these objects. So this PDF document gives us an equation for a point mass. We can see that it's equal to I equals the mass times the distance r from the center of the circle squared. And if we have more than one object, we're going to have to go ahead and add those up for each point mass. In addition, we also have a thin rod that is rotated about its end. And we can see here's a couple of thin rods. Here's the one about the axis of rotation through the end. That is 1/3 ml squared. Let's go ahead and write that down. So for I1, for the rod, 1/3 ml squared. Now for the end masses, I labeled this one 2 and this one 3. So let's go ahead and calculate those. Now the equation that we saw for a point mass, I, for a single point mass, is the mass times the distance from the axis of rotation squared. For mass 2 here at the top, we can see that that's going to be a value, the mass little m, and the distance from the axis of rotation here out to m, that's distance L, so this is going to be L squared here. Now for the third mass right here, we can see that in fact the radius is 0, and so I3 in this case is 0. And so that's what we have for part A. Let's go ahead and look at part B here. So for part B, we're going to go ahead and we're going to have a slightly different axis of rotation. If we look at this one here for B, what we're looking at now is right in the center is our axis. I'm going to rotate right about this, and then we can rotate that thing around about that axis. This remains fixed. Again, we're going to go ahead and add up for the three things to get the total moment of inertia here. So for I1 now, we need to go back and look at the rod, the equation when the axis of rotation is through the center. In this case, it's 1/12 ml squared. And for I2, again, we're going to use the point mass formula. But now if you look at mass 2, here's mass 3, we can see that the distance from the axis here is actually equal to L over 2. So for mass 3, it's also equal to L over 2. So we're going to end up writing down for I2, it's going to be M times L over 2 squared. And for I3, it's the same. It's also m times L over 2 squared. And we can simplify this a little bit as well. That's going to be ml squared divided by 12 plus the contribution from the moments of inertia from the end caps. And if we look real quick, L over 2 squared, of course, is equal to L squared over 4. So we've got, for each of those two, we've got m L squared over 4. If we add them together, we get m L squared over 2. And so we end up having these two equations here for the two different axes of rotation. Now for part C, we're going to go ahead and evaluate what is the moment of inertia in case A and case B when, in this particular case, L is 0.5 meters and capital M 0.35, little m 0.25. Let's go ahead and just plug these values in. So for case A, we're going to have 1/3 capital M times L, which is going to be 0.5 meters squared, plus little m, 0.25 kilograms, times capital L squared, 0.5 meters squared. And we can solve for that and get an answer. And that comes out to 9.17 times 10 to the minus second, and the units for moment of inertia is kilograms times meters squared. So we get that for A. Now let's plug in for part B. Which one do you think is going to have the larger value? Let's check and see. In this case, for part B, the axis through the center of the baton, we've got m times L squared, and so again we've got capital M 0.35 kilograms times L 0.5 meters squared divided by 12 plus little m 0.25 kilograms times L 0.5 meters squared divided by 2. And when we calculate that, we get a value 3.85 times 10 to the minus second kilograms meters squared. And so we can see that the moment of inertia is smaller in case B than in case A. And we could have predicted that in advance because we could see in B, the rotational axis is located in a position where the mass is closer to the rotational axis on average. In case A, more of the mass is further away from the axis of rotation. Therefore, it has a higher moment of inertia in A than it does in B.